folks, and welcome to today's lecture, where today we're going to be talking about multi-electron atoms. So I have a couple of goals for us today. One of those is for us to take the Hamiltonian, which we developed for a hydrogen atom, and see how it can be applied using a series of approximations to an atom that has more than one electron. The second thing we're going to do in today's lecture is that hopefully many of us have been missing our fourth quantum number that we learned about in general chemistry, that spin quantum number m sub s. Today we're going to identify what that quantum number is and where it's coming from, and we're going to show you how we incorporate spin into the wave function. My third and fourth goals are for us to actually do a little bit of review of concepts that we talked about in general chemistry to try and understand them a little bit deeper at a more P-Chem level. We're going to talk about the Aufbau principle and Hund's rule and show how they're used to determine the filling order for electrons into orbitals. And then last but not least, we're going to talk about something called effective nuclear charge, Z effective, and we're going to discuss how it's used to determine periodic properties. So let's get started. Now, a multi-electron atom is defined as a system like you might expect, where there's more than one electron present. The simplest example, and the one that we're going to primarily focus on today, is a neutral helium atom. So it's got 2 protons in its nucleus and 2 electrons. And so we can depict the positions of all relevant particles in this system either using relative distances, which would be kind of the figure at the left, figure A, or what I like a little bit better, it's a little bit more rigorous, putting this whole system onto a coordinate system so that we can see the center of mass fixed at the origin. Remember that center of mass basically is the position of the nucleus, since the nucleus is so much heavier than the electrons. And then once again, we have our positions of our 2 different electrons represented by vectors that either describe the position of the electron with respect to the nucleus, R1 or R2, or the vector that describes the position or the distance between my 2 electrons. That would be R1, 2. And now, if you thought that applying the Schrödinger equation to hydrogen-like atoms was rough, it becomes even more complicated when another electron is added to the system. That's because our electronic Hamiltonian now has to account for all terms that relate to the kinetic energy of the electrons and the nuclei. Now, remember, we're restricting this discussion to the electronic Hamiltonian, and so we don't need to think about the nuclear kinetic energy, but we do have to think about the kinetic energy of each electron, and we have to think about all terms related to the potential energy, which now not only includes the 2 terms that are going to describe the attractive potential energy between my nucleus and electron 1 and my nucleus and electron 2, but it's also going to have to describe for us the repulsive potential energy between these 2 electrons, that because they have similar charges, the same charge, both negative, they're going to repel each other. And so once I account for all of these features, my Hamiltonian, my quantum mechanical operator that represents the total energy of this system, now has 5 terms in it. It's going to have this red term that indicates the kinetic energy of my first electron, a blue term describing the kinetic energy of my second electron, a green term describing the potential energy between electron 1 and the nucleus. Notice that negative sign shows us that that potential energy is attractive. A purple term, that's the potential energy between electron 2 and the nucleus. And then last but not least, a potential energy term between electron 1 and electron 2. And ask yourself, why, unlike the green term and the purple term, is this term positive? And if you need a second, go ahead and pause the video to try and figure out why this is positive. The reason, of course, is that our electron-electron interaction is repulsive. Coulomb's law tells me that if charge 1 times charge 2 determines what that potential is, then if I have 2 negatively charged particles, the overall repulsion, it will be an overall repulsion between those 2. Okay, so if we're going to try and solve Schrödinger's equation, we need to think a little bit about our wave function. And because I have 2 different particles, now each of those particles has to be described in terms of its respective coordinates. So I'll have 3 coordinates that describe the position of electron 1, and 3 coordinates that describe the position of electron 2. Once again, it's easiest to do this in terms of spherical coordinates. The bad news for us is that we in this course, and really in all differential equation problems, only have one technique to try and solve multivariable problems like the one we're working with today. Separation of variables was our one and only shot at being able to solve this Hamiltonian. And the electron-electron repulsion term prevents us from using the separation of variables technique. And so you may have last lecture thought that it was impossible to solve for the hydrogen atom, and what you meant by that was it took a lot of work. It was no walk in the park. When I say that getting analytical solutions to the wave function for the helium problem is impossible, I mean that no one has been able to analytically solve this problem. And so what do we do from here? As chemists, surely we're interested in things beyond just the hydrogen atom. But once you know that this is not an analytically solvable problem, you're essentially left with three different options. And I have some physicist friends, I checked in with them about my snarky joke and they said it was okay. So option one, this is what you would do in a physics class, is you quit here. This would be the end of a quantum mechanics course. Of course, we'd go into a lot more detail about the particle in a box and the particle on a sphere, but this would be the end of the course because this is a system that we can't solve analytically. Option two, and what is going to be the focus of today's lecture, is what I would call the theoretical chemist approach. We are going to try and take this problem and get rid of all the terms that are causing us heartache. In particular, it's this pink term for today. So we are going to make what is a distressingly bad approximation called an orbital approximation, saying let's pretend that the electrons don't actually repel each other. The electron repulsion term we're going to set to 0, and we're going to see if there's still something to be learned about what the shape of these wave functions look like, how our hydrogen-like atomic orbitals might contribute or give us an approach to multi-electron atoms, and it turns out there's actually a lot of rich information to be gained here. So we're going to spend a lot of time on option 2 today. Option 3 I would call the computational chemist approach. And this is what, as practicing chemists, most people use in order to think about multi-electron systems. In this case, we're going to use a number of sophisticated computer programs and software that have been developed over the years to solve for this wave function numerically. We do have to, in that case, incorporate a few modest approximations. No computational chemistry programs are perfect, but they are actually really good. And so even though option 3 is not something we're going to explore today in lecture, it is something that you're going to see show up a lot in our laboratory course that's concurrent with lecture, and something that as we go forward, starting to talk about molecules, we'll bring back to the forefront so that we can talk about some of these computational chemistry tools. But for now, we're going to make some really bad approximations and see where we can go for the rest of today's lecture. Okay, so what happens if we ignore this pink term? That would mean that the last term in our Hamiltonian can be approximated by assuming that, remember, I'm not doing anything fancy here, just arranging some of the terms, that our approximate Hamiltonian is a sum of terms that just depend on my first electron and a sum of terms that just depend on my second electron. And if you notice, this Hamiltonian 1 is identical to the Hamiltonian for my hydrogen-like atom. And we already know how to solve those. And so now that I have an approximate Hamiltonian that's a sum of two Hamiltonians that I already know how to solve, again, bad approximation to just totally ignore this pink term, but we're going to do it anyway. That means that we're going to be able to say something really simple but elegant about what the resulting wave function would look like for this approximate Hamiltonian. And that is that with this approximate Hamiltonian, we've seen an analog of this before in our particle in a box approximation, or not approximation, our particle in a box model, where we saw that when we had a Hamiltonian that was a sum of the x-coordinate, the y-coordinate, and the z-coordinate, that the wave functions were a product of the one-dimensional wave functions, and the energies were a sum of the one-dimensional energies. Here, for our approximation with this non-interacting helium atom where the electrons don't interact with each other, the wave functions now are a product of one-electron wave functions, and the energies are a sum of the one-electron energies. And so what this means for us is that in this limit of the orbital approximation, no electron-electron repulsion, our overall wave function that describes all the electrons in the atom reduces to a product of wave functions that at this point we're coming quite well to be able to understand. And this total wave function, by the way, is something that we would call the overall electronic wave function, or to use more of a GChem-like terminology, the electron configuration of this helium atom. So plugging in some values for our 1s orbitals in particular, because remember, helium, all the electrons are going to go into the ground state, into these 1s orbitals. This would be what our wave function would look like. You may recognize this red and this blue term as our psi 100 wave function. Or if you want to put it in orbital notation so that's a little bit more comfortable, we could say that psi, our overall atomic wave function, is this product of the first electron being in a 1s orbital and my second electron also being in a 1s orbital. And if that looks really familiar to how in GChem we taught you to write electron configurations, it's because that electron configuration is trying to be reminiscent of what this product of one electron wave functions look like. Okay, so it would be really nice to assume that for the helium and for all other atoms on the periodic table, that in order to form the wave functions for atoms with more electrons and more protons, that we could just tack on extra terms to our wave functions that describe each electron slowly filling up the 1s orbitals, then the 2s orbitals, and the 2p orbitals. But it's not quite that simple. We also have to account for the electron spin, and we have to account for the Pauli exclusion principle. You learned about the Pauli exclusion principle in GChem when we told you, as sort of a definition, that Pauli's exclusion principle was a statement that no more than 2 electrons can occupy any given orbital. And if 2 do occupy one orbital, their spins have to be paired. So one has to be spin up, the other has to be spin down. The PChem version, which we're now going to talk about, is that Pauli's principle says wave functions describing a many electron system have to be asymmetric. In other words, the sign of the wave function has to switch under the exchange of any 2 electrons. Now, what does that look like? Let's talk about it a little bit. So first, we should talk about spin before we can talk about antisymmetry of the wave function. There was a lot of good experiments that led to postulating the spin quantum number. One thing I should say about this, because my treatment in this course of spin quantum numbers is going to be fairly brief, one thing I should say is that the spin quantum number is not something that is predicted from Schrödinger's equation. We were trying to predict the behavior of an electron in an atom. We didn't try and account for what that electron was doing intrinsically within itself. The spin quantum number is an intrinsic property of the electron that is not something that Schrödinger's equation can account for. And really, if you ask most physicists, I'm not really sure that they could tell you exactly what spin is. But it's easy to see what the effect of spin is. Electron spin changes the magnetic properties of an electron in quantized ways. Otto Stern and Walther Gerlach in 1921 were the first to run an experiment that showed that we need this extra spin quantum number. Their experiment was essentially to run electrons through a magnetic field, and it can show if that electron is behaving in a magnetic way such that it would be called spin up, or if it would be called spin down. And what they discovered is that these spin quantum numbers, which we're going to label just like in GChem, m sub s, take on quantized values. The overall magnitude of that spin is called the spin angular momentum. It's very analogous to L, our orbital angular momentum term, but the part that gets put into our GChem expressions or our quantum number expressions is m sub s. It can take on values of positive 1/2 for a spin up electron or negative 1/2 for a spin down electron. And so once we have spin, a next question we could ask is, how does that change the wave function? We now have a 4th quantum number, And our wave function should depend on what the value of that fourth quantum number is. But we've done so much work to develop these hydrogen wave functions. We've seen that these hydrogen wave functions can help us understand multi-electron atoms. And so what we're going to do, just like we did with our multi-electron wave function, is assume that these spin functions can be tacked on to the end of our wave function as a product, and that way the spin can be incorporated into the overall spatial part of the wave function, which is what we've discussed up until this point. And so spin functions in quantum chemistry are defined as the alpha function, which designates a spin up electron, or the beta function, which designates a spin down electron. You don't need to know in this course what the exact mathematical expression is for alpha or beta, so much as we need to be able to recognize that that function tells us what the electron is doing and what its spin is. So if I have my 2-electron system like helium, there are different ways that I could put those 2 electrons. Assuming that I've sort of forgotten my GChem and I don't remember the Pauli exclusion principle super well. I could put both electrons spin up. That would be alpha 1, alpha 2. I could put both electrons spin down, beta 1, beta 2. I could put the first electron spin up and the second electron spin down, or vice versa. There's a catch though. One of the rules of quantum mechanics is that electrons are indistinguishable. In other words, there's no way to determine which electron should be spin up and which electron should be spin down. I can't label electrons, and so my wave function should not appear in such a way that would suggest that I could label wave functions. That means that these last 2 wave functions are a little bit problematic, because if I'm going to say that one electron is spin up, the other is spin down, both of the wave functions that I've highlighted right now are these spin functions, suggest that I could do that labeling. So to change up our spin functions a slight amount so that they do account for the property of electrons known as indistinguishability, we need to redefine these last 2 functions as more appropriate linear combinations. And so what you'll notice is that we're going to replace these 2 bad functions, because they don't take into account indistinguishability, with a linear combination where I am adding together the alpha and beta spin functions, and a second combination where I'm subtracting the 2 of them. If you've taken a linear algebra course, this may look familiar to you, because essentially what I'm doing is a change of basis formula. For the rest of us, I just want you to notice that these 2 functions have the property of indistinguishability. If I switch which electron is electron 1 and which electron is electron 2, these functions don't change at all. And I'll have you notice that we do introduce a factor of, in this case, 1 over square root 2, and that's due to normalization. These spin functions, just like all the other functions that we've been dealing with in PChem, need to be normalized so that we preserve the property that integrating over all space gives us 100% probability of finding the electron somewhere in space. No more, no less. All right, so now we have kind of 4 different options for what our spin functions could look like that do obey the property of indistinguishability. But only one of these spin functions is antisymmetric with respect to a change in the wave function. What I mean by that is that if I swap my 2 electrons in this last function, so I take every time I see electron 1, swap it with electron 2, that last spin function is going to turn into a -1 times the original function. We call that antisymmetric, meaning that the interchange, or the exchange of 2 electrons, leads to the function being multiplied by -1. Why do we want this wave function to be antisymmetric? It turns out to be a property of how electrons should behave, and antisymmetry is something that Wolfgang Pauli showed has to be true for electrons. Electrons must be placed in an antisymmetric wave function, and that means that our different products are different product wave functions that take on a form of the overall wave function, again being a product of many 1 electron wave functions, they have to be combined in such a way that the resulting wave function changes sign when any two electrons are interchanged. As you learned in GChem, this principle translates more simply to the statement that no two electrons can occupy any given orbital unless their spins are paired. Because in that unique case, our spatial wave function times our spin wave function, the spatial wave function is symmetric with respect to the interchange of two electrons, but our spin function is antisymmetric. And so if our spins are paired, one spin up, one spin down, then our overall wave function can be antisymmetric. And that would obey the Pauli exclusion principle. Okay, I do want to briefly mention an idea that will show up in the literature called Slater Determinants. And it's a way of showing us more systematically how to generate an antisymmetric wave function. These Slater determinants, if you've taken a linear algebra course, a determinant is a way in linear algebra of taking a matrix and computing a particular property of it called a determinant. And these Slater determinants are a way, if you know how to use linear algebra and determinant language, to always make sure you can generate an antisymmetric wave function given a number of different possible spins that the electrons could be in, spin up or spin down, and the resulting wave functions that correspond to where the electron could be. So in this case, our Slater determinant for the helium atom should involve a spatial wave function, that's the 1s orbital. It's really the only orbital we need to talk about for helium. And then we have a spin up wave function and a spin down wave function. That would give us an overall wave function that is a product of two electrons, each in the 1s orbital, times a spin wave function that tells us that one of these electrons is spin up, one of the electrons is spin down. Okay, so let's go back to our helium ground state and really bring this back to a perspective that we understood from general chemistry. We have two electrons in a helium atom. Both electrons have the same values of n, l, and m sub l, since they're in this 1s orbital, but our magnetic spin quantum number has plus 1/2 for one of the electrons and negative 1/2 for the other electron. And so we can describe this electron configuration for helium as 1s2, where the superscript indicates how many electrons are in that orbital, and where we know from GChem that 2 is the maximum number of electrons that can be in an s orbital. Okay, so we've kind of, through the orbital approximation, talked all that we can about helium, so let's talk about lithium. We've filled up at this point the 1s orbital. Pauli exclusion principle tells us that there are no more electrons that can fit into this orbital, because that would require us to double up on quantum numbers, combinations of quantum numbers that we've already seen before. And so the third electron needs to move into the n equals 2 shell. If this were the hydrogen atom, remember we saw that for those hydrogen-like orbitals, the 2s and the 2p orbitals were degenerate. So for lithium, it's a multi-electron atom. Where's it going to go? Is the 2s orbital or the 2p orbital the next lowest in energy? Turns out you already know the answer to this question from general chemistry. The electron configuration for lithium is 1s2, 2s1, so it's going to go into the 2s orbital. But we should really talk about why it doesn't go into the p orbital. The answer lies with two different factors. The first is something called an effective nuclear charge, which is computed as the difference between the atomic number of the atom that we're interested in minus something called a shielding constant. We're going to have to talk about that shielding constant in a second, because the shielding constant relates to something about orbital penetration. So let's talk about Z effective and shielding first. Electron shielding is, to use one analogy that I really like, is sort of how you feel when you're trying to go to a concert, and if you're like me, are not particularly tall, if you're standing in the front of the room, it doesn't matter how far away you are from the band. You can see everything perfectly. If it's an empty room, same thing. It doesn't matter how far forward or back you are, you can see all of the band, hear the music, just like you would want to. The problem comes when there's a group of people that are standing in between you and the front center stage. In that case, if you're standing in the back, especially if you're short, you are prevented from seeing the full band playing by the people that are in between you and the band at the center. How this relates to electron shielding is that if you envision our nucleus being our band, our center stage, all of the electrons that are spending time in between you, an electron of interest, and the nucleus are canceling out some of that interaction that the electron would normally have with the nucleus. We call outer electrons that are experiencing a kind of shielding effect from the nucleus, we call those shielded. They have a weaker interaction or a weaker potential energy between that outer electron and the nucleus, and we can express that by changing up our Coulomb's law expression to say that the effective potential that this electron experiences a distance r away from the nucleus is now Z effective times E squared divided by our fundamental constants and divided by the distance between those. And Z effective, that's where our shielding constant is going to come into effect. So it's basically saying Z effective is how much less of a strong interaction an electron experiences with the nucleus based on the atomic number of the atom, which should increase the strength of interaction between the electron and the nucleus, and a shielding constant, which tells us how much those inner electrons or those core electrons are getting in the way. And so now that we've thought a little bit about shielding, we can talk about which orbitals and which electrons in which orbitals experience more or less shielding. At the 2s level, our shielding constant appears to be different between the s and the p orbitals. And how we can see that most clearly is by looking at a graph of p of r versus r, just like we did in the previous lecture. And so this graph is shown at the bottom right-hand side of the screen, and the first thing we should plot is the 1s orbital. So these are our 2 electrons in helium that are part of the core electrons. They're closest to the nucleus. Those electrons experience no shielding. They have a strong interaction with the nucleus. Where Z effective comes into play is for the valence electrons, an electron that gets placed in either the 2s or the 2p orbital. And as you might imagine, Coulomb's law says that the strongest interaction that that electron can experience, and hence the most stable that that electron could be, is whichever orbital it could be placed in that has the highest effective nuclear charge. Or, put differently, whatever orbital has the lowest shielding constant, so we can see which orbital allows us, if you like, best access to the center stage and doesn't have us have these 1s electrons get in the way quite as much. So if we compare our 2s orbital, shown as this green curve, to our probability distribution for our 2p orbital, this red curve, you may notice that for the 2p orbital, the most probable radius is a little bit closer to the nucleus compared to the 2s orbital. And the average distance that the electron is away from the nucleus is also a little bit closer in. Those all might suggest to us that the 2p orbital, the electron has a stronger attraction to the nucleus because it's always a little bit closer. That would be true, except that these 1s electrons are constantly shielding the nucleus so long as we're at a distance that's farther away on average than those 1s electrons. And so what matters is mostly, are there times where an electron in either this 2s or this 2p orbital can sneak past the 1 electrons and be closer to the nucleus than the 1s electrons? In that case, that would mean that that electron in that orbital, at least a small fraction of the time, is able to see and interact with the nucleus unimpeded. That would give it a much higher effective nuclear charge, because at least in a probabilistic sense, it means that sometimes it's getting the nucleus's full undivided attention. Looking at our probability graph, that full undivided attention time never happens for the 2p orbital. There's not really very much probability density where you would expect to see the 2p electron closer to the nucleus than the 1s electron. But for this green curve, this 2s orbital, every once in a while, I would say a small but modest percentage of the time, the 2s electron gets to be closer to the nucleus than the 1s electron. We call this effect charge penetration, and it means that during those times, the electron in the 2s orbital can have a very strong attraction to the nucleus. And what happens overall, and I would say I know this more by the results of calculations than I do necessarily by being totally convinced by this graph, the overall effect is that the 2s orbital is lower in energy than the 2p orbital as a result of the different values for z effective that you get for the s versus the p orbital. And again, the different values for z effective come about because there's a different probability distribution for the electrons in a 2s orbital compared to the electrons in a 2p orbital. So as a general takeaway, for multi-electron atoms, both n and l determine the energy of an orbital. And in general, the orbital energies vary such that the s orbitals are lower in energy than the p orbitals at a given n level, are lower in energy than the d orbitals, and are lower in energy than the f orbitals. And a note on terminology that I've been using so far in this lecture, we call electrons, for lithium for example, in the 1s shell, core electrons, and the electrons that are on the outer shell, valence electrons. And for any given element on the periodic table, typically, whatever electrons are in the outermost shell, we'll call that the N max level. Those are ones you call the valence electrons, and any shells smaller than that value of N max, you would refer to those as core electrons. So due to shielding, the energy level diagram for a multi-electron atom shows orbital energy dependence on both n and l. And in this orbital approximation, it's pretty important to note that neither m sub l nor m sub s relate or have an impact on what the energies look like. So here's an orbital energy diagram that you probably saw in GChem showing you the energies of different types of orbitals. You'll notice that for a given value of L, energy increases as a function of n, and also as we change L, we also get an energy increase. And there's a little bit of tension between orbitals that are in kind of these 3 or 4 n levels. What's worse, having a 3d orbital compared to a 4s orbital? Which one would be higher in energy? And you can see it's a complex interplay of, well, one of these orbitals has a higher value of n, that would raise its energy, but a lower value of L, that'll lower its energy. And so often when it comes to ordering the energies of these multi-electron systems, we have to rely on calculations in order to figure out the exact ordering, rather than some sort of heuristic. And it turns out empirically that in most cases, the 4s electrons are lower in energy than the 3d electrons. And so that is going to be an orbital that fills first. When it comes to electron filling, we should recognize the Aufbau principle, which we learned about for the first time in GChem. The Aufbau principle states that if I have an orbital energy diagram, like the one shown here, and I need to fill multiple electrons into this diagram, I should start by filling the lowest energy orbitals and then build up from there. So if I needed to draw an orbital energy diagram for instance, a beryllium atom, I'm going to first put 2 electrons into the 1s orbital, because that's the lowest energy orbital available to me, and then electrons 3 and 4 will occupy the 2s orbital, because via the Pauli exclusion principle, I can't pack all 4 electrons into the 1s orbital, but the 2s orbital is the next lowest in energy, and therefore the orbital that will be filled up with electrons next. Sometimes you'll see these little diagrams online that help you remember the energy filling, and which orbitals fill and which energy. You may also find it easiest to use your periodic table to do that. But remember, this red subscript tells us the maximum number of electrons that can fit into an orbital of a particular type, and this maximum number is determined by our m sub L value. how many orbitals are there of a given type of l orbital. Our s orbitals can both fit a maximum of 2 electrons. Our p orbitals, since I have 3 different p orbitals, px, py, and pz, can fit a maximum of 6 electrons. And then my d orbitals, of which there are 5 d orbitals for each value of n, can thus fit a total of 10 electrons. Once we start filling in more and more of our energy levels, we also need to remember Hund's rule. Hund's rule states that specific orbitals are going to fill up, if they all are degenerate, by having each electron try, if possible, to fill in a new orbital, and then also have all the spins face the same direction. So what Hund's rule would say for something like carbon is that the 2 electrons in these p orbitals, they're not going to both fill in the px orbital right away. One will fill in one of the p orbitals, say px, we don't necessarily know, it could fill in py first, but the second electron is going to fill in a new orbital. The reason that they're going to try and fill in different orbitals, physically speaking, is to reduce electron repulsion. That way they can be far apart in space and thus have a lower energy or a more stable configuration. And again, you can see that from the fact that our px orbital and our py orbital, they occupy different regions of space, and so that means that those 2 electrons are not going to see each other that frequently. It is more complicated mathematically to understand why both of those electrons in the 2 p orbitals for carbon are going to have the same spin. By convention, we normally put them both spin up, although that's convention and not necessarily correct physics. But it does turn out that part of Hund's rule is saying that the energy of the system is lowered when the electrons that are in different orbitals, that are unpaired electrons, both have the same sign. Okay, now if you remember from GChem, and if you may have been noticing from our discussion, that sometimes different types of orbitals can be very close in energy, and you remember now that we're making this orbital approximation, which is a very crude approximation. It means that subtle factors in the environment for a particular element might mean that under certain circumstances, orbitals that are arranged in our very simplistic diagram via the Aufbau principle of kind of 4s is higher in energy than 3d, or sorry, the 3d orbitals are higher in energy than our 4s orbitals, can have exceptions. And so we learned about this in GChem, but I just want to remind us that sometimes in order to get half-filled or fully filled shells, which tend to be a little bit more stable, certain elements in our periodic table, especially in the transition elements, will have exceptions to Hund's rule and Aufbau principle, not because this is actually higher in energy, but because there are certain configurations that can lower our energy slightly. So the overall rule for filling up our electrons into orbitals is that we always want to try and minimize energy. Hund's rule and the Aufbau principle give us suggestions on how to do that, but as soon as we have half-filled shells in the picture, sometimes those give us a little bit of additional stability that we have to account for, and that you might treat as an exception to Hund's rule or the Aufbau principle. Okay, so where I want to end us for today is that all this discussion of multi-electron atoms can help us start to understand not just the properties of helium or lithium, but really what the properties of any atom on the periodic table might look like. And so our periodic property trends, and this is something that we're going to explore a lot more both in lab and in lecture this week, is about how concepts of Z-effective, the Aufbau principle, and Hund's rule, but mostly Z-effective, help us understand periodic property trends. 2 trends that we're going to focus on for this week are the ionization energy, where we take an element, we take its highest energy electron, and we remove it entirely from that atom to give us a cation of our element, and an electron that is, again, as indicated on the right-hand side of this balanced equation, completely removed from the atom. We know that as we go left to right on the periodic table, Z-effective is increasing. And that means that the outermost electrons are seeing more and more of this effective nuclear charge. So the ionization energy is getting larger and larger as we go left to right on our periodic table, because the effective nuclear charge is increasing. And via Coulomb's law, that means it's harder and harder to remove that electron. We can also see in terms of periodic trends that if I start talking about successive ionization energies, so I have a first ionization energy where I remove one electron, and a second ionization energy where I take the resulting cation and I remove a second electron from it, that means that my second ionization energy is going to be even bigger than the first, because Z effective is increasing as each successive electron is removed, because each time I remove an additional electron, there's less and less shielding for the remaining electrons. The last property that we focused on in GChem and that I want us to revisit over the context of this week is the electron affinity. In many ways, electron affinity is a reverse process compared to ionization energy. We're going to take an element and we're going to add an electron to it and end up with an anion. As Z effective increases, the electron affinity becomes more and more significant, more and more exothermic, because the Z effective tells me how much positive charge an incoming electron will see. And the more positive charge there is, the more that atom will experience an energy stabilization via Coulomb's law if an electron is located nearby that atom. All right, so that's all that we wanted to talk about for today. I would say the takeaways from today's lecture is that we saw how to approximate the Hamiltonian for a multi-electron atom. We learned that we needed to account for electron spin in order to explain this tension between the Pauli exclusion principle, telling us that no two electrons could share the same quantum numbers, and the fact that each of our orbitals can hold up to 2 electrons. We talked very briefly about Slater determinants as a way of helping us systematically navigate how to put together my spatial part of the wave function and my spin function in order to come up with my total wave function for a multi-electron atom. And then we revisited a couple of concepts from GChem that were really important for us in thinking about atoms. The Pauli exclusion principle, the Aufbau principle, and Hund's rule all help us understand how many electrons in an atom would populate an energy level diagram in order to give me my overall electron configuration. Okay, so that's all that we've got for today, and I will see you folks in lecture. Looking forward to it. Take care.